Determine all values of c that satisfy the conclusion of the mean value theorem for the function f of x equals the square root of x on the interval 1 included to 9 included. The first thing to do is to determine whether the two conditions are met for the mean value theorem to apply. The first condition, the function f of x, which is the square root of x, needs to be continuous on the closed interval given. The square root of x does not exist everywhere. It is required that what is under the square root has to stay greater than or equal to 0, so x has to be greater than or equal to 0. The interval given is 1 to 9, which is not going to be negative ever. It's definitely greater than 0. And therefore, this function will be continuous on the closed interval from 1 to 9. Closed means that it includes both endpoints indicated by the square brackets on both endpoints. Condition 1 is met. Condition 2 is on the derivative. Before we take the derivative, let's rewrite f of x as a fractional exponent. The square root of x is x to the first power second root, x to the 1/2 power. F prime of x will be the power rule, bring down the power. Subtract 1 from it, I will call it 2/2, which gives 1/2 x to the 1 minus 2 negative 1/2 power. Since we have a negative exponent, we can rewrite this by moving it to the denominator with the 2 that's already down there, and it'll be x to the positive 1/2. And positive 1/2 power is the square root of the x. We need the derivative to be continuous. It's called differentiable on the open interval. 1 over 2 squared of x does not exist everywhere. First of all, the x is under a square root, so it cannot be a negative number. It has to be greater than or equal to 0. But here, it's in the denominator, and the square root of 0 is 0, and 2 times 0 is 0, so x cannot be a 0 because that will make 0 in the denominator. So x has to be greater than 0. It can't include it. Once again, the interval is 1 to 9 here, and that is greater than 0, so it is okay on this interval, and therefore we are continuous on the derivative, known as differentiable. And it's always the open interval for the differentiable. It does not include the endpoints because functions are never differentiable on their endpoints. Open means it doesn't include the endpoints indicated by round brackets on the endpoints. So condition 2 is also met. Since both conditions are met, the conclusion of the mean value theorem does apply here. It says that the slope of the tangent line at some value c equals to the slope of the secant line connecting the two endpoints, f of b minus f of a over b minus a. And this will hold true for at least one c, maybe more, in the open interval of 1 to 9. In this problem, the interval is 1 to 9. The left endpoint a is a 1, the right endpoint b is a 9. So the right side here can be written as f of b, which is a 9, minus f of a, which is a 1, divided by 9 minus a 1. The left side, f prime of c, can be determined by plugging c into f prime of x. That will give 1 over 2 square root of c, and that will equal f of 9, and f of 1 can be evaluated with f of x, which is the square root of x. The square root of 9 for f of 9 minus the square root of 1 for f of 1 over 9 minus 1. The square root of 9 is a 3, minus the square root of 1 is a 1 over 9 minus 1, which is an 8. 3 minus 1 is a 2 over 8, which can be reduced to a 1 over 4. So 1 over 2 square root of c will equal 1 over 4. We can now cross multiply both sides by 4, which will put a 4 in the numerator on the left, and multiply both sides by 2 square root of c, which will put a 2 square root of c in the numerator on the right. We can divide both sides by 2, so 2 equals the square root of c. And we can now square both sides to solve for c. Two squared equals the square root of c squared. 2 squared is a 4, so we have 4 equals the square root of c, and then squared is c. So it looks like we have a c value of 4. We only want to keep those c values that are in the open interval between 1 and 9. We're guaranteed at least 1, maybe more. We ended up with only 1 value here, but it's in the interval. And therefore, c equals 4 is the value of c that satisfies the conclusion of the mean value theorem.